At the house right now. I can't see you guys, so.
Yeah, around 20.
20 people, wow.
Yeah.
Nice, that's a sizable crowd. Awesome. I want to ask a question first. Actually, two questions. Who here in the house is currently working on autonomous worlds?
Yeah, almost 20 people.
20 people. Yes.
Yeah.
Nice. Okay. Full house. Second question. Who here in the house has heard about CRDT or understands how it works?
Yes. Barely. Holy shit.
Oh, four people is understanding CRDT.
I'm working on this.
Oh, two.
4 people. Awesome. Okay, so yeah, that's actually better than I expected, because usually my experience has been that CRDT is something that's quite unfamiliar with the blockchain people, but we're at a good start. So my talk will not be expecting anyone to have any pre-existing understanding of CRDT, so don't worry if you don't know what it is. Okay, the talk today is about real-time autonomous worlds on the CRDT Superhighway, and I am Gyoza from Topology. Let's get it going. Okay, so we have a full house working on autonomous worlds. I think everyone here is familiar with the article that defined the term autonomous worlds. It's from Xerox Park. It's defined as worlds that have hard diegetic boundaries, formalized introduction rules, and no need for privileged individuals to keep the world alive. Okay, so the first definition, hard diegetic boundaries, is basically using computer programs to specify what is in and what is not in the world, period. Number 2, formalized introduction rules means that also you use computer programs to specify in which ways you can introduce new stuff into the world, okay? And the third thing, no need for privileged individuals, is that this program does not need permission to be run and to be enforced by any particular people. It is enforced by default by random people, by people you don't know, but you have guaranteed that these rules are enforced by default, and that is autonomous world. We want to argue that although it has a blockchain origination, it does not have to be fully on-chain, and we argue that by leaving the blockchain centrism, we can build much better autonomous worlds and probably fulfill its actual potential. But before talking about autonomous worlds, we have to talk about time. And time is a really tricky business, right? Time is tricky in this reality, in physics, and also tricky in computer science. You have a picture of Bitcoin clocks. The reason we put Bitcoin clocks in here is that Bitcoin can actually be understood as time, right? If you look at the original the Bitcoin paper, it says Bitcoin actually is a timestamping server. There's a network of servers that timestamp things that happened to the network. And as a result, Bitcoin is the time that ticks forward, transaction after transaction, blocks after blocks. But notice that it is a linear notion of time, right? It is a straight line where everything that happens on Bitcoin is situated on this linear time. Or to put it in another way, if you take 2 transactions from Bitcoin, you can always tell which one happens before the other one. It's either A after B or B after A, period. So that's a linear notion of time. However, in 20th century, we have learned that in our reality, time is relative, right? The notion that time is absolute and linear is something that was invented by human construct and formalized by Newton, and this was in the 1600s. But by 1900s, we have realized and accepted that time is relative. So this is the very famous train thought experiment. Who here in the room understands or recognizes the train experiment, thought experiment? How many people here?
Around 10.
Awesome, 10 people. So I can briefly go over it. So imagine you are in a train and there's a light bulb in the center of the train. Okay. And imagine two people standing on either ends of the train. Now, if you turn the light on, you will believe that these two people will see the light at the same time because the light is situated in the middle of the train, right? However, if you observe this situation from outside of the train, where a train is moving in one direction, you would think that one person will see the light first because of the relative velocity. That light actually travels of a shorter distance to the person that's at the back of the train, right? So the idea that's established by Einstein is that the notion of simultaneity is relative, or the notion that if things happen at the same time or they didn't happen at the same time is relative to your perspective or your point of view. It's relative. Now, this is actually tremendous because we can allow a network computers to run a universe way faster than if we respect a linear notion of time. In other words, if we go relative, we can go super fast. And there is a computer science construct that basically formalizes that thing, and that is called CRDT, or conflict-free replicated data types. Now, I think this talk is not technical, so I will not go into the technical details. But I will say that if you want to understand CRDT on a high level, you can understand it as multiplayer data types. Or these are data types that you can use to write computer programs. And these data types are multiplayer by default. And so your programs will be multiplayer by default as well. That basically allows you to make multiplayer network application super easy. Another way to put it is CRDT is putting the internet into the data, right? If we think about the web, the internet, we are putting data onto the internet for people to discover it, for people to request it. But CRDT reverses that paradigm by putting data into the internet. This is into the data, which is tricky to imagine. But if you imagine really hard for one moment, if you have internet inside the data, that data itself is networked, it's distributed itself. It's like an octopus with many tentacles reaching in different directions, and people can access the data at the same time and interact with it at the same time. The data is networked by default. It has internet built into itself. So that is CRDT. Now, to prove our point, we built a prototype last year using YJS, which is a off-the-shelf open source CRDT library in JavaScript, on top of WebRTC, which is a technology that allows browsers to talk to other browsers peer-to-peer directly. And also using Phaser, which is a browser-side open source game engine, so that we can do physics stuff and we can do rendering stuff. The result is this. Our prototype ran at 30 frames per second. And this is not some blockchain TPS thing. Every penguin you see here is controlled by a user from their own laptop. And all these laptops are connected directly peer-to-peer. There's no server in the middle. There's no blockchain in the middle. It's just laptops connecting to laptops. And you have guaranteed that everyone is looking at the same thing, with penguins hopping around in a 2D Super Mario-like world. Okay, what's more interesting is if we can do collision. Collision here means two penguins can collide and they will not pass over each other. The way we did it is super strange. We did it in a collaborative manner. The idea is that if you and I are in the penguin world, and if we collide, I will back myself off and I will send you a mail, put the mail in your mailbox. And if you process the mail, you should also back yourself off. That way we are collaborating and resolving this collision. And the result is this. So you can basically play Pikachu volleyball with this because these players are colliding with each other. Let's watch it again. Okay, and again, this demo was done, I believe, in a public WeWork using the Wi-Fi at the WeWork. And this was two laptops connecting to each other directly. We also presented this demo at the Local First conference, which just happened at the end of May in Berlin. Local First conference is the conference happening right now that is sort of at the forefront of the entire CRDT research circle. And we also demonstrated the world with the author of YJS, who also is living in Berlin, and he enjoyed controlling a penguin a lot. Okay, so what's next? We implemented something using off-the-shelf library. What's next? We want to make a protocol. We love it so much that we think this should be the default way of building multiplayer applications on the internet. Or to put it another way, this technology, this paradigm, should be formalized into the internet protocol stack so that just like HTTP, just like HTML, in the future, people should be making multiplayer applications as easy and trivial and commonplace, just like how we talk about HTML and HTTP nowadays. So we have a rough idea of what a protocol stack may look like. It builds on top of the TCP/IP stack. We have the P2P messaging, where computers talk to each other peer-to-peer directly. On top of that, we have causal consistency, which is not something I will go into in this talk. But if we have an Ask Me Anything session, I'm happy to answer any question. And on top of that, we have CRO. And CRO here is CRDT, drop the data type and put object at the end. You have CRO. It is an object. If you make smart contracts on blockchain, you're familiar with smart contract. Right? Coming to our protocol, if you want to make something, you will take CRO and you will make a CRO for your own application. That's CRO. If you look at the lab, there's TLC, which I will also not introduce. It's basically a distributed clock, on top of which you can do consensus mechanism, and on top of which you can do snapshotting and compaction. Snapshotting is important because you want to save something from time to time and maybe also put it on blockchain, if you will. Compaction is important because it's pruning. And if you don't prune stuff, it grows super fast and it grows out of control. So it's pruning. For those of you who understand how the Mina blockchain work, Mina has pruning built into its protocol in a similar way. This illustration shows how CRO should work among a network of computers. So you can look at Alice, Bob, and Charlie. They both have CROD, which is the purple diamonds. So these three computers have the purple diamond CRO. No one else have it. And actually, no one else is interested in it. If you're interested in something, you subscribe to it, and you will learn about all the updates about it. Otherwise, you don't subscribe to it, and it does not concern you. You don't have to have memory or network bandwidth to run it on your site if you're not interested in it. If you look at this and you think about a monolithic blockchain, the monolithic blockchain does not work this way. On a monolithic blockchain, if you run a full node of the blockchain, you are synchronizing the entire blockchain, the entire state, the world state of the blockchain. And what is in the entire world state? It is every smart contract on the blockchain that ever existed. So millions and millions of smart contracts, the most of which you're not interested in. But in order to participate in the blockchain, you have to synchronize all these smart contracts. With our protocol, you care about what you care about. You don't care about other CROs. So that gives you scalability, and that gives you low coupling, which is important to have this be scalable and secure. And on top of that protocol, we prototype a node, and we build a demo on that node. So this demo is in 3D and it's built directly on top of our protocol's implementation. And we just demonstrated this in Brussels at the ECC. This is how it works. So you hop around in the 3D world and you come to a wall, you pick your stickers and you put your stickers on the wall. And this entire wall is one big CRDT where you can collaborate and graffiti together. Every player is playing from their own laptop, and these laptops are talking peer-to-peer with each other using the lib peer-to-peer library. For those of you who may have heard about IPFS, Protocol Labs is behind IPFS, and Protocol Labs also built a protocol suite called libp2p. We are actively using it and building on top of it. Okay, so the use case that we imagine this protocol can enable is the cozy web. The cozy web is the idea that we're not supposed to always hang out on public social networks where whatever you say can be seen by everyone in the world. Most of our traffic actually happens on Telegram and email threads, Discord server. These are the cozy parts on the internet where we can hang out with people we know and we trust. With CRO, we want to facilitate that you can hang out with people you want to hang out with full agency, and you can actively shape the environments and spaces where you hang out together, because it's peer-to-peer and it's sovereign to yourself. And these spaces should be interoperable. They are not platformized or behind any walled garden. They can connect and communicate with each other by default. The idea is that this is the schematic of the web, or the World Wide Web. And this picture was taken from, I think, 1990s, and one of the earliest World Wide Web documentation, where the idea of the web is that you have websites or hypertext documents, and the material they're made up of is HTML. HTML is the material you use to make hypertext documents. And you would serve the hypertext document from server so that every client can request from you and access the document. And the way that people request these documents from you is via the HTTP protocol, the hypertext transfer protocol. This is already formalized into the internet protocol stack. Our vision is that the protocol we're working on together, and also with the community, in a few years of time, deserve to be formalized into the internet protocol stack, so that in the future, making P2P multiplayer applications that you fully control, you and your community fully control, should be as easy as making an HTML website, put it on a server for people to HTTP request it. As easy as that. The roadmap for ourselves till the end of this year, until September, we are working on publishing a paper. We want to produce a V1 of the protocol specification. We want to work on anti-cheat, or more formally, Byzantine fault tolerance. We are working on a TypeScript node already, but we are also aiming to build a Rust node and have these two nodes interoperate so that networks can run any kinds of nodes they want and they interoperate. And excitingly, also very challenging, is to put game physics inside a CRO so that the physics is enforced as inside the CRO. If we can do this, then by DEFCON in November, we want to be hosting hackathons and welcome everyone to take CROs and make whatever that interests you. But it's going to be peer-to-peer multiplayer and hopefully in real time, and it's going to be very cool. Okay, so the question is where to join the cool kids that are actively working and discussing this. We have a Twitter. You can follow for all the updated news. Discord QR code, scan to join below. The GitHub also below, QR code, scan to join. The GitHub has the paper there, and it also has the implementation and the specification there. Everything is open source and free access. We are doing community calls. We just did one last night. We're going to do the next one in 2 weeks, August 7th. And if you're interested in working full-time with us, our websites have open roles that we're actively looking to fill. So this is it. This is what we're working on, and we're excited to discuss any parts of it. Thank you.
Hey, Gyoza, I appreciate your great presentation and the demonstration. I really would like to play your demo we're in Brussels. I really like the sticker games because, yeah. So would you mind taking your time for answering the Q&A session in this room?
Where are the questions? I'm looking. I'm sharing my screen now, so I can't see it.
Oh yeah. Hey.
Hey, my name's Ozzy.
Hey.
I'm a huge fan of CRDTs, working on some stuff on that as well. What do you think of the Farcaster CRDT?
Nice. Yeah, this is an insider question, I think. So Farcaster, one funny way that a friend taught us to pitch our protocol is our protocol basically is Farcaster as a service or FAS. The idea is that Farcaster, let me just search it. You guys can see my screen now, right?
Yes.
Okay, so if I just search Farcaster Hub, go to image, you can find this thing. Okay. Okay, this thing. So Farcaster consists of contracts on chain, Ethereum, or Optimism to be particular. And then they have the off-chain thing. But when you talk about on-chain and off-chain, it's as if you are blockchain-centric, right? Because if you are more neutral to technical architectures, you have one blockchain part and the other is not blockchain. But what is it exactly? This off-chain part is running a big CRDT. It's a big CRDT that has the user accounts, the posts, the likes, the follows, and so on and so forth of the entire social graph, which the Warpcast client is taking from and rendering as a user interface for you to access. The open social graph really is the power, but I think there's some problem with the Warpcast client having some centralized power over it because they're developed by the same company and they have a lot of resources. So I think there's some difficulty in the reality of running a decentralized or pushing for a decentralized protocol. But I think the idea is super neat. And hopefully, with topology protocol, you can take one CRO and you can implement it as an open social graph identical to the Farcaster social graph. That way, and you can also modify it for whatever social graph, or it doesn't have to be social graph. It can be relationship graph. It can be different kinds of graph as long as it interests you.
Very cool.
Thank you. Hey.
One more question.
Sure. Could you speak loudly?
Loud?
Yeah.
I will try.
Okay, thank you.
Yeah, so my question is about WebRTC and exposing IP address of the user. So when WebRTC is used, IP address is exposed. Maybe some kind of tweaks to hide it, but I see that the privacy issue or if it is P2P and if it is not realize that. I don't know if I will loud now.
Hey, Guilty. Could you hear that question?
I didn't hear the question, sorry.
I can repeat it.
Oh, okay, thank you.
He basically said that when you're using WebRTC, you're exposing IP addresses, and he's wondering if you figured out a way to build a relay system where it's much more privacy conscious when you're using WebRTC.
Mm-hmm. I think that's an important concern. That's actually not our current priority. I think we want things to be super easy to build with and run with sufficiently good performance real time with a lot of people play at the same time. I think the anonymity part is something we'll tackle later. I think this is a very important idea. And I think if you look at the history of the web, it wasn't built with one group of people. The web was built in a very distributed manner by many people. So I believe that if CROs are actually useful for making fun applications, people who are very privacy-centric will take it and implement end-to-end encryption with it, which I think is compatible with the architecture that they have. Does that answer your question?
Oh, yeah, sorry. I think the speakerphone was a little broken and out of control, so we couldn't listen to your answering in detail.
He basically said that that's not their main priority right now, although their protocol, you can build encrypted CROs on top of it and enable a much more privacy-preserving environment for it. But their current WebRTC does not enable hiding IPs. Huddle One, which is another sort of company, is building a decentralized WebRTC. I think they approach this problem as well. So I think that might be interesting.
Yeah, let's share information. Thank you.
I think the idea for the protocol is to focus on making CRO useful and also collaborate with other protocols at different layers, at the web transport layers and so on, so that we can work together. The topology protocol is not going to be a vertical stack of a bunch of things. It's going to be really focused on making CRO useful Yeah.
Any questions? Okay.
Hey, it's Tim Cotton.io. Question for you on just the number of clients that a CRO can support in an optimal case. Are we talking like 5, 50, 500? Where does the path of communication break down between common words?
Yeah. So we have not stress tested this, and I think we have not been prioritizing improving the concurrent user count of a CRO. I think there are many factors to it, and one factor could be network topology. If you have a topology where every peer is connected to every other peer, a fully connected mesh, that is not really scalable.
Really?
And there are other things as well. Basically, how much recompute you have to do. So in our current architecture, or in our current implementation, you would be hearing about everything that everyone else did in the past when they arrived from the network at your client, and you would execute their operation to move the state forward. And so all the computation is happening in a redundant manner at the edges, at the peers. And that may not be the most scalable method because you have a lot of repeated computation. And so I think that is one scalability opportunity, is to try to reduce the redundant computation there. I will not drop the ZK keyword, but I just dropped it. I think there are different ways to look at it, and that's not currently our priority. I think at least for the next few months, we want to make CRO work at least for 10 to 20 people. I think that is a lower bound. Easy to spin up, 10, 20 people come in and interact in near real time just by default, and you can easily modify it. I think that is our short-term goal.
Okay, makes sense.
Oh yeah.
Then,
Okay.
can you hear me from here? Okay, so one of the questions that I had was with regards to distributed physics. So if you have like a mesh network, and let's say there's a non-negligible latency, let's say about 200 milliseconds, from node, let's say just for 2 nodes. Okay, back to the collision case. So if a person collides with person B from his frame of reference, person B does not know it's being collided. Then person B receives a collision signal 200 milliseconds later. And so during this time, there's basically a conflict in terms of the frame of reference. So how is this going to be resolved?
Yeah. So I think I heard 76% of what you said, and I think you're referring to this, right? In physics.
I can repeat. So basically, like if you have this kind of system where the collision is done locally, and you have a network latency of, for example, like 200 milliseconds, how do you handle cases where, like, by the time you receive, the fact that collision happened,
Yeah.
it might be like too late, or like might cause like weird these things?
Yeah, this is common to network games. I think if you play, I believe Street Fighter has P2P mode. I think if you play multiplayer fighting games, it's a lot of the fighting games netcode is written to run between 2 computers directly. In client server games as well, right? You would have the situation where on my screen, I thought I moved there first, but maybe in a few frames or a few dozen frames later, the server corrects me, saying that actually the other person moved there first. And so we collided and I could not have moved there. And you would have netcode that corrects for that. You can roll back and reevaluate what should have happened correctly. The key here is not about avoiding the rollback, because the speed of light is actually pretty slow. We are talking about interacting across the internet on planet Earth. And speed of light only travels, I think, a few inches. You can calculate this, a few inches per CPU cycle. So CPU ticks in cycles, right? And every time CPU ticks, if you measure how long the light travels, it's only a few inches, but the internet is covering the Earth hundreds of kilometers. So we have to accept that information travels takes time, and we will be doing things that later will be conflicting, and we have to correct that conflict. The key here is not to avoid this, unless we have some technology to transmit information much faster than light. But until we have that, we need to embrace conflict and talk about how to resolve that. Now, the way blockchain resolve conflict is by assuming every transaction by default conflict with every other transaction. I'm not talking about the vanilla blockchain, not the kind of the McLeese or parallelization stuff. The conventional blockchain assumes every transaction is conflicting with every other transaction. And so you're making blocks of transactions, proposing how to order them, and you're basically voting for blocks to be accepted. When you're ordering transactions, you're assuming that they all conflict, so they need to be carefully ordered, which happen first and later. With CRDT, the idea is that, okay, you don't do voting ordering stuff. Instead, you write in the CRDT spec what are the possible conflicts that can happen, and what is the policy that every honest actors should follow to resolve the conflicts. And if every honest actor resolve the conflicts in the same way, they see the same thing. They will not have a situation where one guy moves to this grid, but from the other perspective, the other guy moves to that grid. You won't have divergence. And then the BFT part basically is saying, what if some actors are presenting they're bad actors? If the CRDT is BFT, then you can have the honest actors all see the same thing, despite the fact that they're bad actors doing bad stuff to it. So I think that's the whole picture.
I have a question. So what if like some player joins the game and does not follow the algorithm?
So this is the BFT side. And there are many kinds of bad deeds or bad things you can do to a CRDT. And I think they should be carefully examined. And this is a very big topic. So one bad things you can do to the CRDT is by sending operations that don't make sense for the application, right? Like your application may have 10 different functions that can be invoked, but a bad actor is invoking a function that does not exist. And this is the easy case. Every honest actors will just parse your function and say, oh, this function I don't recognize, so I would ignore you. And maybe also, honest actors will ban the bad actors by doing so that the bad actors do not pollute the network moving forward. Everyone just stop listening to that and stop gossiping the message over the peer-to-peer network. There are other bad things you can do that is more tricky, such as you can publish something that has causal ordering that is malicious. But this touches upon causal ordering, which I did not cover in the talk. And for those of you who may understand what causal ordering is causality, is cause and effect, right? It's if I do something and then I do something after, then the thing that I do later is causally depending on the thing that I did earlier. That's causal ordering. Now, bad actors may say, I'm doing something depending on something very long time ago in the past, pretending that the thing he just did actually happened a long time ago. So in the game, the bad actor can say, hey, I actually headshot you 1 minute ago, so you should be dead by then. You shouldn't be alive now. And this is the bad thing. You're claiming to do something in the past where you actually just did it now. And this is actually more nuanced than how I just described it. But in the paper that we're going to publish and in the BFT part of the work, this will be actively handled. One way to do is to time out things. So if we introduce a linear time in the CRDT, we can use that time as a security clock that says, okay, if you do something, and if you claim that that thing happened too long ago, 1 tick or 2 tick or 3 ticks ago, then it didn't matter. So that clock serves as a security clock that is timing out things. And once you have a timeout, you cannot claim anything that you did before the timeout. Does that make sense?
Is it clear for you?
Okay. Any questions?
No, I just want to read that part. That's part of the paper I actually care about.
What does it mean?
Oh, yeah, he wants to learn more about the topic in detail, but it's just not.
Okay.
I'll learn more in detail about your call to ordering and tick resolution because that's actually really interesting on figuring out how you keep the window pure and keep people from managing to say something happened 3 ticks ago. I'm actually very curious about that. So cool.
Cool.
Yeah, super cool. So thank you for your presentation, Yuto Gyoza.
Thank you for having me. And I think I was added to the Telegram group, so I'll be happy to answer any question there.
Yeah. Thank you.
Cheers.
Cheers.
Thank you, everyone.